Hello, welcome back. So previously we looked at the basics of temperature. What is temperature? What are the kinds of thermometers? And what are the scales that we use to measure temperature? Those three things. So by now you would have enough knowledge to try out some past years. So we're going to do, I think, 4 of them here. I recommend if you have not tried them, pause the video and go try them out first. It's more effective that way, you know. You try and then you realize, oh my goodness, I have no idea how to do this. Then you come and we do it together. Otherwise, you just stare at me doing stuff and who knows whether you remember anything. Okay, first thing, what is meant by the statement that two bodies are in thermal equilibrium? So the very first thing we looked at was some ideas. Okay, let's say there's 2 objects equal mass, but one is at 28 degrees, the other one is at 16 degrees. There's going to be some heat flow from here to here, but there's also going to be some heat flow from here to here. So in this case, there's not thermal equilibrium because there'll be a net heat flow from left to right. But thermal equilibrium means that if they are in the same temperature, there should be no net heat flow. So maybe if this is 30 degrees Celsius and this is 30, yeah, there's some heat flow from left to right, there's some heat flow from right to left, but the net is 0. No net flow. So let's write that out. The statement: regions in contact are in the same temperature. That's the first thing. But also you must say that same temperature, so what? So there is no net flow between the bodies. Alright, so same temperature, no net flow, or 0 heat flow. That would be a B1 mark for thermal equilibrium. Now we come to an interesting one where you have to choose a suitable thermometer for the scenario. Okay, well, this is the fun part. We kind of have a bit of practice in the previous video. So suggest suitable types of thermometers, in each case to measure the flame of a Bunsen burner. Now this is pretty hot. You probably don't want to choose something that will melt or break when you put it in the Bunsen burner. So I have broken test tubes by putting them on the Bunsen burner before, so probably not the glass ones. So one of those that can have a very large range and can stand the heat of the Bunsen burner could be the resistor or resistance thermometer. I don't know, some people call it resistor thermometer. What other ones could we use? Well, we learned 4 main ones, but there's actually more. If you know more, you can write them. As you notice in the mark scheme, you see some other weird thermometers. Never mind, just stick to the 4 that you know. So one is the resistor thermometer, or the thermocouple works fine as well. These are metal-based probes, so it wouldn't melt as easily if you stick it in the Bunsen burner. So any of these would work fine. Yeah. Okay, next one. The change in temperature of a small crystal when it's exposed to a pulse of ultrasound energy. Now, I don't really know what the temperature is on this one. They didn't tell us, is it hot, is it cold? I don't know. But the important keyword is a change in temperature. There are not many thermometers that measure change very quickly and very well. And if this is a pulse of ultrasound, it's probably a instantaneous change. Pew! Suddenly it's hot, suddenly it's cold. I don't know. So maybe I would think of something that can measure changes pretty well. So my top choice I would choose is thermocouple. Okay, thermocouple. Because thermocouple measure changes pretty well. And also the thermocouple can measure very small things because the tip of the probe is very small. Some of you may argue, how about the resistance thermometer? Well, the resistance or resistor thermometer can't measure things that change as quickly, so I don't know. I wouldn't put that. Okay, so thermocouple is the best choice for small things, quick change in temperature. Okay, let's move on. Some water is heated, so the temperature change from this to this. What's the change in temperature in Kelvin? So the question is, do you want to convert to Kelvin first and then only find the answer, or do you want to straight away minus? Well, it doesn't matter because Celsius and Kelvin, the change is the same. So let me write out for you. Let's say you are lazy and you say, can I just do 38.0 minus 26.5 in Celsius? Okay, so this is delta Celsius. Can. You will get 38 minus 26.5, 11.5, which is also the change in Kelvin. Because, like, if you remember how to convert, You want to convert Celsius to Kelvin. What do? You add 273.2 and you add 273.2 to this side. So the 273.2 will cancel out, so they don't really matter. But if you want to be very strict and write everything in Kelvin, sure, you can convert and write it out. So if you want to do everything in Kelvin, you got to convert it first. Then this will be 38.0 plus 273. There's only one decimal place, so we're going to do one decimal place. Minus the other thing, which is 26.5 plus 273.2. Okay, so you don't believe me? You can type it out again, but you'll get the same answer, 11.5. So either way works lah, huh? Okay. 11.5. Keep those decimals, just 1 mark. So as long as your answer is good, you're good. The final temperature in Kelvin. Now this is a temperature, not a change. So you make sure that your readings are in kelvins. So just now we have what? 38 degrees Celsius. We need to convert this to Kelvin. So you just add 273.15 or point what? So if this is only 1 decimal place, then you have to round off to 1 decimal place as well. So it's 273.2. And you get 73.2. What is that? 311.2. So that's right here. Okay, be 1 mark. Only 1 mark for conversion. Okay, so that's just this first part lah. Basics on how to convert and what kind of thermometers to choose. Okay, let's go to another one. Ooh, interesting. There's a graph. May-June 2006 paper 4. Electrical resistance of a thermistor is used to measure temperature in the range of that. Oh, thermistor. Miss, we didn't learn thermistor in the thermometers. You kind of did. Well, in AS, it used to be in AS, but thermistors are the kind of special kind of resistor with this symbol. Okay? When it's hot, their resistance go down. Hence, this graph is called a negative temperature coefficient. So, a quick rewind. If we go to the previous section, thermistor can come under the class of resistance of wire, kind of. Okay, because the kind of thermistor is based on the resistance of the resistor, special resistor. So normally, the higher the temperature, the higher the resistance for all these ones here. But thermistor is going to be the other way around, so just add on here. Thermistor, our dear thermistor, as you may remember from AS, is going to look something like this. See how that's different from all the other metals, nickel, copper, platinum? Thermistor is going to be going down, so more resistance means you're very cold. Cold resistance. It's like thermistor, LDR, and things like that. Anyway, here's the graph that's given to us. So, let's go. Okay, let's go. So state and explain the feature which shows that the thermometer has a sensitivity that varies with temperature. What's a sensitivity? How sensitive? What does it mean to have a sensitive thermometer? It means that if you have a very small change in temperature, okay, change in T, you can see it by your change in R. So ideally, if it's very sensitive, if you have a very small change in temperature, you have a big change in R. Then you can see suddenly the resistance changed a lot, then you know, oh, the temperature has changed. So this is what we call a sensitive thermometer. So if we're looking at this graph, we're trying to understand how does change in T over change in R relate. We can think of ratios, my friends. So if we use this ratio, delta R over delta T, or I should say, a better way of saying it is dr, a small change in R, small change in T, dr dt, which is also the gradient of this graph. Okay, that is an indicator of sensitivity. So if you look up here, maybe I look at this point, the gradient is pretty steep. Okay, so if I look at this change in R, change in T, this is dt, dr. Then if I look down here, it's like a little bit different, not as steep. So this is my dr, it's my dt. That's called a changing sensitivity because it's curved. So we need to describe that down here. So the first thing to say is the gradient. Oh, we need to state and explain now. Oh, okay. So maybe we state first. What is gradient? So what is sensitivity in terms of the graph? So gradient is a measure of sensitivity. One way to know whether it's sensitive or not. Okay, so your gradient is dr dt. So gradient is measure of sensitivity. Okay. So how do we know that sensitivity is changing? Gradient is changing, no? So we can write that down as our second point to explain our point a little bit. So the graph's gradient is changing. Or you could say it varies with temperature. The higher the temperature, the less steep it is, no? So varies with temperature. Okay, kind of 2 points here. So one is for this, one is for this. I guess you call them B1 marks, one for each. Okay, so remember sensitivity. Ideally, for a small change in temperature, you have a big change in resistance. Okay, that's how you can measure that. Very small changes in temperature. So I would say up here is where it's more sensitive, down there is where it's less sensitive. Okay, at one particular temperature, the resistance of the thermistor is 2040 plus minus 20. Wow, got uncertainty here. Determine the temperature in Kelvin to an appropriate number of decimal places. So it's kind of a conversion question here. You're going to have your 2040. Okay, so how are you going to convert that to Kelvin? You need to look at the graph law. 2040 is where you look for it. 2040 is... Wow, this is a bit small. Let me rub off this thing. We zoom in a bit, ma. Computer, why you hang? There. So this is 2100. So you have how many boxes? 1, 2, 3, 4, 5. Which means 2040 will be here. 2, 4, 6, 8, 10. Okay, so this is 2040. And that will intersect the graph right here, which will go down. And we go and check, what's the temperature there? So let me scroll all the way down to this. 15. Is this Kelvin or Celsius? Celsius. Oh, must remember to convert. So we put our 15 here. Probably should put a decimal too. How you know to put decimal? Because the smallest division of this graph is a decimal. Okay. You see, if I go over here, this is 15.2, 15.4, 15.6, 15.8, 16. So there's a 0.2, 0.4, 0.8, and I should probably include that. Okay, let's also include the uncertainty. Why not? Since it's good practice. So the original uncertainty is 2040 plus minus 20. Okay. So plus minus 20, that will be down here and up there. You know, this is kind of like paper 5, you do uncertainties. So just to double check, this part of the question actually doesn't need uncertainties, but I just want to show you how to deal with it on graphs. My, there's many lines. Okay. It looks like it's very nicely 2 boxes. So that will be 14.8 and 15.2. So plus minus 0.2 also. Okay, nice and sweet. 0.2 Celsius. But we want the temperature in Kelvin. Well, maybe there's a later part of this question that asks for uncertainty, but we don't need to find the uncertainty, but just so you know, this is how it looks like. So 15.0 plus, convert to Kelvin, 273.2. That will give me 15 plus 273.2, 288.2 Kelvin. Now they give you a very nice reminder, appropriate number of dP. So make sure you round off your dP of your conversion factor, because here is only 1 dP. So here should also be 1 dP. You follow your raw reading. Okay, 2 marks for this. It's not written, actually no, 3 marks actually. 3 marks? Very nice. So if you got your reading from the graph, that is actually 1 mark already. If you know how to convert properly. Okay, this is your second mark. Okay, and your decimal round correctly. Okay lah, one more mark lah. Okay, well, make sure you know how to convert. Okay, these are like 3 marks. Let's do a few more. 2 more here. This one's kind of interesting. Page 7. The resistance of a thermistor, again thermistor, is 0 degree at 3840. At 100 degree, the resistance is 190. When the thermistor is placed in water, its resistance is 2300. Assuming the resistance of the thermometer vary linearly with temperature, calculate the temperature of the water. Huh? How to measure? What is going on? If you're not sure, just list out a table. So you have resistance on one hand. And what do you have? Temperature of the water, right? Wow, that line. I think my lines are getting... Okay, I give up. Never mind. So at 0 degrees Celsius, if this is 0, you read 3840. Then at 100 degree, resistance 190. So the question is, when you put at the water at don't know what temperature, your resistance is 2300. What is the question mark temperature? Is what it's asking you. So you have 2 values. Now, don't say, I can just use ratio, right, miss? Yes, ratio, but ratio of what? Don't simply ratio. You need to know what you're doing. Okay, think about this one. If you can solve this out without me giving you the answer, this is good. It'll be good practice. So the key lies here. We are assuming, you know, the thermistor is not linear lah, but we are assuming it varies linearly with temperature, which means if you plot a graph of this resistance change with temperature, something like this, okay, something like that. At 0 degree, you are 3840, so somewhere here, lor. At 100 degree, you are at 190, so maybe somewhere here. Okay, so your graph will be a straight line, linearly, ma. You assume linearly, so it's like that, lor. Okay, and this is 100. This is 0. Now the question is, at 2300, what will the temperature be? So you can think, oh, 2300 is somewhere where? Here, I guess. What will be the temperature? Question mark, question mark. So linearly means the gradient is not changing. Gradient unchanged means you can take whatever triangle you want as long as you take ratio of gradients. So what I'm going to do now, there's a few methods to do this lah, but one way I'm going to do is this. So I'm going to say, okay, let me look at these 2 data sets. And I find the gradient from that. Do you remember how to find gradient of a straight line? So gradient here will be 190 minus 3840. That's on the y-axis. Over 100 minus 0. So I'll find a certain gradient value. Now that gradient value will be the same as if I take maybe these 2 data points and find gradient again. Or if you want to be different, you say, miss, can I take the first and the last one as a gradient? Can also. Up to you lah, whichever one you want to use. Okay, as long as you compare gradients. So let me just take these 2 for you. So this will be 2300 minus 190 equals to, don't know what temperature is this, I'll call it T minus 100. Okay, so you're saying, this method that I'm using is saying, oh, if I draw gradient triangle here and then another gradient triangle here, gradient should be the same. So I find for T lor. So here I should get T down there. It's a delta T, by the way. So what I can say is, oh, I just noticed an error. Negative sign. Yeah, here got negative sign. My bad. Finding gradient should be y2 minus y1. So this should be 190 minus 2300. Terbalik. Backwards. 100 minus T. Okay. Alright. If you're wondering where 190 comes from, 190 is down here, lor. At this point that they gave to us at 100 degrees. This is 190. Okay, minus everything, should get a temperature of 42.2 degrees Celsius. In Celsius, right? The answer? Okay lah, 42.2 lah. Celsius. Oops. So this is 2 marks. The first one is if you know how to find the gradient, something like this. Do you write something like that? Then the last one is if you use the gradient to find other things. Okay. So to recap, the main idea is just saying that, okay, if it's a straight line graph, if it's linear, means the gradient is constant. And how do you find the gradient? Y2 minus Y1, X2 minus X1, also known as delta R over delta T. So as long as you take any 2 points, your delta R over delta T should be the same ratio. So this is the ratio that you want, delta R over delta T. Okay, next. I think this one we can still do. We'll save part B for later. The temperature of the water, same water, right? Okay. Temperature of the water is measured on the thermodynamic scale is 286 Kelvin. By reference to what is meant by thermodynamic scale, comment on your answer in number 1. What is there to comment? Well, they told us this thing you originally measured, 42.2, is measured with what? Thermistor. Okay, on the Celsius scale, thermistor. But if you use a thermodynamic scale, temperature, maybe the Kelvin one with the constant volume gas thermometer, I don't know, is 286. Are they the same? Is 286 same as 42.2? I don't know. Let's check and see. Okay, this is a clue. They say on another thermometer is 286. So let's see. 286. What shall I convert? How much is this thing in Celsius? Let me just calculate real quick. So 286 minus 273.15. I just write everything lah. Okay. What would that be? Actually, let's not do the 0.5. This will give us 286 minus 273. 13 degrees Celsius? That is way different from 42. Okay, if I convert 42 to Kelvins, this would be 42.2 plus 273. If I keep 3 SF, 0.2, 315. Oh. that does not match. Why? What is happening? So on one thermometer, I measure this. Another thermometer, I measure that. Why is this problem here? That's what they're telling me to explain. Comment on your answer in number 1. 3 marks. Wow. So the first mark already comes from here lah. If you show a conversion, either this or this, you're trying to convert to compare the temperatures, that is a B mark. So you notice our thermistor temperature is a bit too high, 42 degrees Celsius when it's actually 13 only. What is the problem with our thermistor? So you need to say, is our thermistor a thermodynamic scale of temperature? What does this mean? So we talk about the definition of that. So you need to say what a thermodynamic scale is, and that is thermodynamic scale doesn't depend on property of substance. Okay, you're looking at the energy of particles and things like that. So doesn't depend on the property of a substance. Now, what does a thermistor depend on? Think about it and see. Thermistor is a resistor, right? You're measuring what? Resistance, right? The previous one. We're measuring resistance and use resistance to indicate what temperature it is. So that is what we call the property of a substance, resistance. So thermodynamic scale doesn't depend on that now. So you get 13 degree lah. But what's the problem? You see our problem here? We are assuming that resistance varies linearly with temperature, which is not exactly true lah. Because you see this. Before this, the question already see the graph is not linear already. So is this also a thermistor? Yeah, this is also a thermistor. Not linear, so our assumption is wrong. So you need to write that down. So change in R. Okay, resistance is with temperature. I should also mention with temperature is non-linear. So we have the wrong assumption there. So 1 mark is for the conversion to compare on top there. Second mark comes from your understanding of what a thermodynamic scale is. It doesn't depend on the property of a substance. That is the M1. So you say the problem. Oh, change in R with T is non-linear. Just a final mark. Wrong assumption. So you see lor, like that lor, they will ask you compare. Actually, the water temperature is 13 degree. Why your thermometer measure 42? Then you must say, oh, because must be lor, non-linear lor. R doesn't vary linearly with T. So our assumption here is wrong. It's okay. It's part of life. We do wrong things and we realize it's incorrect. Okay, I'll save this part for later. You can do it after you've learned the later section. Let's do one last one here about calibration of thermometers. ON11 P43. Now you have two thermometers, a resistance thermometer, a thermocouple thermometer, you have to remember what those are both used at the same time to measure a water bath. Explain why. Although both thermometer calibrated correctly, Eddie, they may record different temperatures and their equilibrium. Wow. So water bath is here, you got two thermometers sticking. Wow. Thermometer resistance, yeah, I don't know how to draw, just draw something like that lah. Okay. Thermocouple, I guess you stick one in here. I assume it's already calibrated, so it's the type where you don't need to stick it in a different reference liquid. Okay. Why they calibrate correctly, Eddie? Why they can measure different things one? 2 marks. Explain why. So you remember how these things are calibrated from the stories that we talked at earlier? Well, we use calibration curves, right? For the thermocouple, that is EMF against temperature. Okay. For the resistance thermometer, is resistance against temperature. That's our calibration curve. So when you calibrate, usually you pick two fixed points. Okay, so for example, your resistance thermometer, maybe you pick this point here and this point here. I don't know. Then you like, oh, draw a line. Okay, so I calibrated already. I assume any reading in between, if I see this resistance, it should be this temperature. Now the EMF versus temperature one, also you just like kind of find 2 points and then you're like, oh, here's a thing, here's another one. Okay, maybe the graph look like this based on those points. So assume that everything in between is here and here. Okay, but there's one thing you need to know. This that we draw is the real reality graph. When we calibrate, we usually assume that they are linear. Like this assumption that we did just now. We assume it's linear lah, then we do. But if they are not linear, then your things are wrong lah. Although your calibration points are the same, maybe water and ice, but in between maybe it's actually curved like this. Maybe it's curved like that. I don't know. Maybe this one is curved like this. Maybe this one is curved like that. You don't know. So you have to explain the calibration problem. So calibration, firstly, we assume that it's a linear change lah. So calibration assumes a linear change of property. If resistance is changing linearly. If EMF is changing linearly. Property with T. Okay. But the reality is, as we see in the previous video, EMF and R don't really change linearly with temperature. So you say, but both properties, R and EMF, do not vary linearly with temperature. Okay, so just remember, calibration, we are assuming it's a linear change, but in real life, like the graphs that we showed you, it's not linear. Calibration assume a linear change. Okay. 2 marks. 1 mark comes from the assumption of how we calibrate when we do fixed points and calibrate things. And then also, you need to talk about, okay, both properties, though, are not linear. So that's the second point. Okay. Now I want to comment on one thing. In one of the textbooks, where is the textbooks? Let me see if I can find it again. This one. Yes. There are some summary texts that say, where is it? A summary of all thermometers. There. So they talk about the platinum resistance thermometer down here. They say linearly. And yeah, it's linear for most part if you use platinum. Okay, thermocouple is Not linear already lah, okay? So the note about platinum, the resistance thermometer, is it really depends on what metal you use and what's your range. So when we did this originally, we draw this shape because we're like, I don't know, maybe your wire's a bit different, okay? But the graph shape depends on metal range. So here are some examples. So the textbook, when they say platinum is linear, I'm guessing they're looking at like here until here. It's mostly linear. After that, you see it start to increase. Then in different metal, different shape. I don't know, maybe another metal, your shape is like that. Maybe another metal, the shape like that. So it really depends lah. But the point is, it can be non-linear. Okay. Let's continue to the last part of today's examples. Wow, very long, miss. Yeah, lor. All paper 4, like paper 2 kind of stuff. State in what way the absolute scale of temperature differ from other temperature scale. What's the absolute scale of temperature? It's also known as the Kelvin scale. Mr. Lord Kelvin. How is it different from the others? So you can say that this one does not depend on the property of a substance. It measures directly internal energy law, so does not depend on property. Maybe other scales are calibrated with ice and salt and I don't know what nonsense. But this one doesn't. So that's the first thing. Absolute scale of temperature from other temperature scales. Okay. Then they'll ask you what is meant by absolute zero. 0 means 0 Kelvin or negative 273.15 Celsius. What does it mean? Well, you already say it doesn't depend on property of substance. It's more on the energy of a system. So you can say it is a temperature, I shortcut a bit, where the atoms or particles in the system have 0 energy or minimum energy. So this is one of the definitions you want to remember what absolute zero is. Absolutely zero. Can we achieve this in real life? Not exactly. We've got very close though, but it's very hard to have absolutely zero. Okay, last one, a conversion question. Very similar to the one we did before. Temperature of water bath increased from this to this. Determine in Kelvin appropriate number of SF. They remind you, please remember to round properly. Okay, determine the Kelvin of 50 degrees. So here you have to be very careful already. You see, oh my, this is 2 decimal place. Which means when you convert from Celsius to Kelvin, you need to plus 273.15, also 2 decimal place. Because you have to match your raw data. So here you add, you get 323.15 Kelvin. So just write 3. Must write the whole thing, right? Yeah, no, because they already tell you they want appropriate decimal place. So 1 mark here. The change in temperature of the water bath. Change in temperature, you don't need to convert to kelvins, but if you really want to, sure, you can go ahead. So if you convert to kelvins, you'll be 353.15 minus 323.15, all in kelvins, so you get about 30.00 Kelvin. Why 00 then? 15 minus 1500 lor. So you put 30.00 Kelvin. If you want to do Celsius, make sure you write it out. 80 minus 50 or 80 minus, why 80 again? 50. 30.00 Celsius, which is the same as this. So you can only do this for change in temperature. Okay. So I think that's all. The bunch of examples here to better understand how you can choose your thermometers, convert scales, and talk about calibration and a bit of sensitivity as well. So now you can go and check out. I think this is the end of chapter 11. So the next part will be all chapter 12, where you start to look at the kinetic theory of solid, liquid, and gases. You got your tools, got your thermometer. Let's use it to study physics now. See you in the next video.